Hi all. In this video I'll be talking with you about how to graph polynomial functions and what we need to know about their behavior at x-intercepts and stuff like that. So we know that whenever we write polynomial functions, they can be any degree. They could be a quadratic like this, they could be a fifth degree function like this. But typically whenever we write them, it's standard form to write them in decreasing order if it's in non-factored form. That just makes it easier for the user to see what's going on. I can see that this is a quadratic function by seeing that the first term is x squared, and I can see that this is a fifth degree function again by seeing the first term. And knowing some information about what that leading variable is going to tell us a lot of information about the graph, and we'll be talking about that as we go throughout the section. Now, in both of these problems, we could also represent them in factored form. The factored form actually tells us a lot more information than the non-factored form. These two problems that I put up here actually factor to these two expressions. Here I can see that this expression 4x squared minus 4x minus 15 has factors of 2x plus 3 and 2x minus 5. And the second one has factors of negative x squared times 3x minus 1 times x minus 4 times 2x plus 1. Now, what I'm wanting us to be able to do by the end of this section is realize that any polynomial that you can factor, you can graph. And in fact, you can graph it pretty easily. So here's the things we're going to be talking about. So first of all, we know that in order for a polynomial function, x can be only raised to a positive whole number exponent. The polynomials are characterized by the degree. It's just the highest powered exponent in there. We know that the domain for every polynomial is negative to positive infinity. And you can graph out a polynomial with a smooth curve. It's never going to have any gaps or asymptotes or anything like that. Polynomial can have at most one fewer turning point than its degree. So whenever you look at a quadratic, we always know that they have a vertex. We've already been graphing quadratics. They always have a vertex, which is the turning point. So anything degree 2 is going to have one turning point. And you can say, well, that's one less than whatever the degree is. And if it's of higher degree, that doesn't necessarily mean this one's going to have 4 turning points, but it could. It could also have 2 turning points, or it could also have 0 turning points. We'll talk about all those scenarios. So first of all, just some basic graph functions. If you see a flat line, we know that that's just y equals some number. In this case, it might be like y equals 3. We call that a constant function. Linear functions are functions that have the same slope and a given y-intercept. We've been graphing parabolas, or the graph of a quadratic, that'd be degree 2. Degree 3 functions, you can automatically recognize them as because they have opposite end behavior. If one side is pointing downward, the other side points upward. This is going to be x cubed most likely. A quartic equation goes back to an even function. All even functions are going to end up having the same end behavior. In this case, I drew a negative quartic, or a negative fourth degree function. We'll talk about more about how we would know that later. And degree 5 function, this would be a negative degree 5 function. It's going to start high and finish low and cross the x-axis 5 times in this case. Now, let's talk about that end behavior. How do I know whether one side points up and the other side points down? What I'm going to do each and every time is just look at the leading coefficient. Like I was saying up here in this problem, this is a negative odd function. It has odd power x to the 5th, but its leading coefficient is negative. All negative odd functions are going to start high and finish low. This is a positive even function. I already know when I graph it, it's going to start high and it's going to finish high. Very similar to that right there. And this negative 6x to the 5th looks very similar to this one right here. Now, the way that you can keep that in mind is in my little information down here. I tell you that if you have an even function, if its leading coefficient is positive, you might as well just think of it as its end behavior is going to look the same as y equals positive x squared. If it's a negative even function, it's going to look the same as a negative x squared. It's going to start low and finish low. If it's a positive odd function, You might as well think of it as like positive x cubed. It starts low, finishes high. If it's a negative odd function, it's going to start high and finish low, like I said this one right here did with the negative 6x to the fifth. Now let's look at some specific examples here to try to make this a little bit more concrete. If I ask you to determine the end behavior of the following polynomials, and you're supposed to state your answer as an end behavior sketch, in other words, just like we did on the other page. If you're given something like this, 18x minus 9x squared minus 2x cubed, don't let the order of the problem confuse you. The leading coefficient is always the coefficient in front of the highest powered variable. So when I look at this, I can say, well, x cubed, that's an odd function, and this is going to be a negative odd function. In terms of the end behavior, I can just ignore that part and say, well, it's a negative odd function. So negative odd functions, every negative odd function in existence is going to start high and finish low. Now, over here, it's a little trickier as far as the end behavior because you're going to need to understand the leading coefficient is what happens when you multiply all the highest powered of x's. So if you took x squared times 3x times x, that's going to give you 3x to the fourth. And so you say, well, that is a positive even function. Every positive even function in existence starts high and finishes high. So it's going to look just like that. Now let's analyze those two functions a little bit more and talk about their zeros. The zero of a polynomial, we might also call it the x-intercept. The zero for a polynomial is any x value which is going to give you a zero y value. All zeros are found just by setting your function equal to 0 and solving for x. So I say it usually involves factoring. A zero is characterized by its multiplicity, the power of the factor giving the zero. And that's going to really impact the look of the graph at that specific zero. And we're going to talk more about that later. First of all, let's go ahead and concentrate on how do we find zeros. So if I ask you to find the zero of this polynomial, well, by the very name, you say, well, the zeros are when it crosses the x-axis or when it's equal to 0. I set the function equal to 0. Now this one's not too easy to set equal to 0. I have some factoring to do. So you notice the first thing I did is I rearranged it in descending order. Then I factored out an x. Once I factor out that, and in fact I factored out a negative x so I could make that leading coefficient a positive 2 instead of a negative 2. I didn't want to start off with a negative. So I have a positive 2x squared and then plus 9x minus 18. So then in order to show my work over here, when I'm trying to set this equal to 0, I need this fully factored. I went ahead and said, well, let's use the AC method. I took a times c. 2 times negative 18 is negative 36. I needed to find factors of negative 36 that added together to get to a 9. So I said, well, negative 3 times 12 is a negative 36. Negative 3 plus 12 is 9. So then I take those two values and I expand the middle term. The plus 9x becomes minus 3x plus 12x. So then, once I do that, and the whole reason for doing this AC method is it should create a 4-term polynomial that is easily factorable by grouping. So you'll see I grouped the first two and I grouped the second two. I took the greatest common factor out of the first group, which is nothing more than an x, left you with 2x minus 3. I looked at the second group, and between 12 and 18 I could factor out a 6, and not surprisingly, yet again left me with 2x minus 3. So I already had the factor of negative x out front. Now I've factored out a common factor of 2x minus 3, and what's left over when you factor that out is the x plus 6. You set all three of those factors equal to 0, you'll get x equals 0, 2x minus 3 is equal to 0, which you can see results in a solution of 3 over 2, and x plus 6 equals 0 results in a solution of x equals negative 6. So I was supposed to determine the zeros of the polynomial. All three of those are zeros. Now, you could have expected or expected as many as 3 solutions, and I got all 3. I know that that's all my solutions. I go over here to my second problem, and I have it already factored out. So since it's already factored out, I can set each factor equal to 0. If x squared is equal to 0, then x is equal to 0. If 3x plus 1 is equal to 0, then 3x is going to equal negative 1. And then I can say x is equal to negative 1 over 3. And then finally, again, the x minus 6 is equal to 0 is going to add 6 to both sides and give you x equals 6. Now, the next page builds off of this, but it's going to talk about what happens at each of these x-intercepts. So I'll go ahead and show this page, but I'll keep the other page handy here. This page talks about the multiplicity of a 0. So that's how many times it's going to or how many times that solution is going to occur. So like if I had in this last problem, you'll see I had x squared is equal to 0. You could have factored this left-hand side and said, well, x squared is x times x. So x would equal 0 and x would equal 0. Anytime that's the case, or anytime the factor that's raised to a power is equal to a number, then what you're going to be able to say is this solution occurs with multiplicity 2. All the rest of my solutions here just occurred with multiplicity 1. They came from a factor to the first power. I solved, no problem. The only one that's different is this one right here because it came from a factor that was squared. Now notice, what's going to happen whenever that's the case, I'm talking about the multiplicity of a 0. If it comes from a factor that's just to the first power, it's just going to cross right through at that x-intercept. But if it's coming from a factor that's to the second power, and you might remember this by just saying, hey, it behaves just like y equals x squared. Y equals x squared touches at the origin and it goes back in the direction it comes from. So wherever the 0 is at, the graph is only going to touch at that point and go back in the same direction. If it's any odd power, it's always going to cross, but if it's not a multiplicity 1 where it's crossing straight through, it's going to do more of a sliding pattern, flatten out as it gets towards the x-axis and then start going back up steep. You should think of that as like the behavior of y equals x cubed going through the origin. And then in my last portion, if it's any even power, it always touches and goes back in the direction it came from. Generally, the higher the even power, the more it's going to flatten out and then go up quickly, or in this case, go down quickly away from the curve. Now, when I'm looking back, this is referring to the same problems that we had on the other page over here, where we had 18x squared minus 9x squared minus 2x cubed. Notice, in this one, it's just asking us to determine the x-intercept behavior for these polynomials. So I've already found out the x-intercepts, and I already found out that they all just occurred once. So what I would say here is, since all the x-intercepts just occur once, the graph is just going to cross straight through each one of them. So that's the pretty simplistic scenario. It's just going to go right through. Now, for the other one, though, for g of x equals 0 is what we call it had a double root because it came from the factor of x squared. So root multiplicity 2 is often the way that this is referred to. And anytime that a solution or a 0 comes from a root of even multiplicity, it's just going to touch at that x-intercept and go back in the direction it came from. So I would just say the graph is only going to touch at x equals 0. It will not cross there. But then my other two zeros just came from first degree factors. No problem. They're just going to cross straight through at those x-intercepts. Okay, now let's look at a problem from beginning to end and graph it all out together. So whenever we do this, guys, what you're going to need to make sure that you do is kind of follow these steps. It really helps out. The first thing that you need to understand is that you need to know what the this LCT, that's the leading coefficient test. That's what we discussed on the first page. You can go in and say, well, the leading coefficient test, if it's a positive even function, it starts high, finishes high. If it's a positive odd function, it starts low, finishes high. Negative even starts low, finishes low. Negative odd starts high, finishes low. So you're going to do that first. Notice I go into this problem down here. That's the first thing I did. I saw that it's going to be a negative odd functions. Every negative odd function in existence starts high, finishes low. Then you locate the zeros and their multiplicities. So all I did is I set this function equal to 0, and I said, well, since it has 4 terms, I could factor that by grouping more than likely. I grouped the first 2 and factored out a negative x squared out of that group and was left with positive x plus 2. In the second group, I factored out a 4 and was left with x plus 2. So then you have the common factor of x plus 2 that can get brought out. My other factor, I chose to put the constant first. You could have said the other factor is negative x squared plus 4. Well, negative x squared plus 4, it's the same thing as 4 minus x squared. The reason I wrote it this way is it makes it easier to further factor that using difference of squares. I said 4 minus x squared can be factored further into 2 plus x, 2 minus x. A squared minus b squared is equal to a plus b times a minus b is all I've done there. But now I see that that first factor, the 2 plus x, that's the exact same thing as x plus 2. So that's better written as, instead of x plus 2 and then times another x plus 2, that's just x plus 2 quantity squared. And then I have my times 2 minus x there is equal to 0. Once it's factored, you set each of your factors equal to 0. So I have x plus 2 is equal to 0. Move over the 2, you'll get x equals negative 2. But now please understand that 0 came from a factor of even degree. So I came down here and said that factor occurs with multiplicity 2. My other factor, 2 minus x equals 0. I add x to both sides and I see x is equal to 2. Now that one just occurs with multiplicity 1. Anytime it's multiplicity 1, you don't have to state that. The only times you need to state it is when it's something other than 1. So now it was asking me, once you find your zeros and their multiplicities, make a rough sketch. So I'll go in here and say, well, my rough sketch, I need to locate the x-intercepts or the zeros. They're going to be at negative 2 and positive 2 over here. And then I can say, I know that my function started high, finished low. So whenever I began starting or drawing this function, I went ahead and started with the up arrow. And then I said, I know it's going to come down and it's going to have an x-intercept at negative 2. But unlike a lot of x-intercepts where it's going to go through, it's going to touch and go back in the direction it came from. So I actually started drawing this from the x equals negative 2, and I knew that that was going to be a minimum there. So I said, draw this like y equals x squared based at x equals negative 2. And then it's going to go up a little bit until about x is 0, but I can't keep on going up. And the reason I know I can't keep going up is because I have another x-intercept at 2. So it's going to hit a maximum usually about right in between your two x-intercepts. So I went up, don't worry about how high that goes. I went up to a point here, and then I started coming back down. And we're interested in the behavior at the x-axis, so we say, well, at the x-axis, at x equals 2, this root occurred with just multiplicity 1, which means it crosses straight through at x equals 2, and we can finish up that graph. Now let's look at a couple others that are more fun than that one. So this one I'm asking you to sketch the graph of the polynomial. I give it to you in factored form. X times x minus 3 times x plus 4, quantity squared. First thing you would need to do is understand what the end behavior is with the leading coefficient test. I said x times x squared. It's going to be a positive x to the 4th. All positive even functions start high and finish high. So I knew the end behavior from the very beginning. And then I set each factor equal to 0. X equals 0. X minus 3 equals 0 gives me a x-intercept at x equals 3. And x plus 4 equals 0 gives me an x-intercept at x equals negative 4. But I know that that 0 is going to occur with multiplicity 2. And so now I can say, okay, that 0 occurs with multiplicity 2, the others were just multiplicity 1. So it's going to cross at 0, cross at 3, touch at negative 4. So I go ahead and I plot my x-intercepts, negative 4, 0, and 3 in there. And then I knew I had to start up high. I came down, I touched at negative 4. It's going to go up, it's going to hit a maximum right in about negative 2. It's right in between these two x-intercepts. And then it has to start coming back down to the next x-intercept. But at that next x-intercept at x equals 0, it's going right through and crossing. It's going to hit a minimum value approximately around 1.5, and then start curving back up to hit the next x-intercept at 3. And I know once it hits that x-intercept, it's just going to keep on going right through because that one also occurred with multiplicity 1. Now for my last one here, or at least last one before the application problem, if I ask you to sketch a graph of x plus 5 to the 4th times x to the 5th times x minus 3 to the 6th, first thing I want you to do is multiply the terms of x. You would have x to the 4th times x to the 5th. That would give you x to the 9th, and then x to the 9th times x to the 6th. That would be 9 plus 6, and you'd get the 15th power. So we can say, okay, all of the terms of x would multiply to be x to the 15th, and that's a positive x to the 15th. All positive even functions start low and finish high. So I can say, okay, I know that my function starts low, I know it finishes high. It's going to have x-intercepts when each of these factors equal to 0. So that's going to be at negative 5, at 0, and at 3. Now, the factor at negative 5 is of multiplicity 4. What that tells you is your graph is going to touch at negative 5. Well, the graph at 0 has multiplicity 5. That means it's going to cross at 0, but it's not just going to go straight through. It's going to slide through at 0. It's going to flatten off at 0 and then go through. And then the x-intercept that's at 3 occurs with multiplicity 6, which again just means it's going to touch at 3 and go back in the direction it came from. So as I start my graph, I know I would start down low. So I would go to the left of my first x-intercept at negative 5 and say, okay, I'm starting down here. Now I know it has to go up and touch the x-axis at negative 5, so it's actually going to hit a maximum value at negative 5, 0, and then it's going to turn back downwards. It's going to hit a minimum value right in between these two at approximately negative 2.5, and then it's going to start coming back up because it has another x-intercept at 0. This x-intercept at 0, though, is an odd one, so it is going to cross, but it crosses in a sliding pattern. So you'll notice I flattened off before I got to 0, stayed flat for just a little bit after, and then I had to go on up. Between 0 and 3, the next x-intercept, it's going to get large till about 1.5. Then it's going to have to start coming back down towards the x-axis again. It touches at 3 and goes back in the direction it came from. Since 3 was a root of even multiplicity, it had to touch and go back. And please notice your end behavior matches what it was supposed to match, which is pretty cool there. Now, the last page of this section here, if I look at an application problem with you, I'm wanting us to look at a box that's made from a rectangular piece of cardboard. The cardboard measures 40 by 60. I'm wanting us to form a box that would have a maximum volume using these using the surface area we have from this cardboard cutout. So I can say, well, okay, if I'm going to form a box, I need to keep in mind that every time I make a fold, I'm going to be losing a portion of that box because of how I have to fold it in order to create the box. That's what I've tried to show in this second picture here. What I'm going to lose in each dimension is whatever the height of the box is going to be, and I'm letting the height of the box equal x. So if I let the height of the box be x, its length here, it was 60, but now it's going to be 60 minus x on this side, minus x on this side. That's why I'm calling that length 60 minus 2x. Same thing for the width. It was previously 40, but now it's going to be 40 minus x on this side, minus x on that side, so I get 40 minus 2x. So when I say the volume of the box is length times width times height, that'd be 60 minus 2x times 40 minus 2x times x. Now all I've done here in this first one is I went ahead and FOILed out these two. 60 times 40 was 2400. Then I would have minus 120x minus 80x, and then I would get plus 4x squared. All of that is multiplying the x that comes next. So what I did from here to here is I went ahead and distributed that x throughout that, and I wrote it in descending order. Typically we want our answers in descending order, so I said you'll have a 4x cubed. We know that we'd have a total of minus 200x in here, so that became minus 200x squared when I multiplied by x, and then plus 2400x. So this is my volume formula for this box that's going to be created. Now, when I ask what's the domain of the function, typically we say, well, hey, it's a polynomial, so the domain is all real numbers. Not so here. You need to keep in mind that none of these dimensions could ever be a negative value. So I just went in and I said, well, I know that the height would have to at least be 0. So if you just have the normal box, I mean, without even folding it, I guess you could technically call that a box. It wouldn't have any volume though. So you could let x equal 0. It certainly could not be a negative number. But then the greatest x could be is to where your dimensions could not be negative. And so you'd say, well, your most restrictive dimension is your width. So 40 minus 2x, I said that width, 40 minus 2x, could never be a negative number. So I said must be greater than or equal to 0. I added 2x to both sides. So that gave me 40 must be greater than or equal to 2x, which means x has to be less than or equal to 20. All I've done is I divided by 2 on each side. Now that needs to make sense to you here. X does have to be less than or equal to 20, because think about what if x was 20? Because then if x was 20 and the height of your box was 20, you wouldn't have any material left for the width of your box. Your width would be 0 because it'd be 40 minus 2 times 20. And so in that case, your volume would be 0. So I know at each number in my domain, the volume of the box would be 0 if x is 0, and it would be 0 if x is 20. If x is anything beyond 20, it just doesn't make sense, because then you would have a negative width in your box. So that can't happen. So now I went down and I graphed this function out. In order to graph it out, what I did is I used my reasonable domain there to help me out in the problem. So let me show you what I did. I typed the function into y1 on the calculator, the 4x cubed minus 200x squared plus 2400x. So I just typed the function into y1. Then all I did, anytime you know what the domain for x should be, you just go to your window and you'll see I already have it entered in, but you just say 0, enter, 20, enter. And then for the y values, all you have to do is hit zoom 0. That automatically fits the y values to any x values that you choose. And you see your graph looks something similar to what I have drawn out on my sheet here. In order to find out that maximum volume, we can say, well, now again, it should make sense here that this is a volume formula. When I try to plug in a 0, it's going to say, well, the volume is 0 because you don't have any height in that scenario. If I try to plug in an x value of 20, yet again, it's going to say your volume is 0 because in that scenario, you wouldn't have any width to your box. So we need to find the height that generates the maximum volume. That's the x value of the vertex, and then the corresponding y value. In order to do that, I just hit second calculate maximum. Left bound. You could scroll around, or you also know clearly 0 is on the left bound of that high point. I'm just going to cheat and say, hey, 0 is my left bound. Right bound. Well, you know 20 is on the right side of that high point, so I'll just hit 20. Guess, I just hit enter again. And then you'll see it's telling you your maximum between 0 and 20 is this point right up here. And it's going to be 7.847. You'll see I rounded to 3 decimal places. And the y value is 8,450.447. Rounded to 3 decimal places again. Now, you do need to be able to interpret this answer. Please remember, the y value is always the maximum. So I would say this box attains a maximum area of 8,450.447 cubic inches when we allow the height of the box to be the x value here. X was the height of my box when the x is, or when the height is 7.847 inches. Okay, so this section was trying to make you more comfortable with graphing polynomials, and then we did the quick application with the box with the polynomial. Hopefully that gets you more comfortable with these problems. You can let me know if you have any questions.